Hi, welcome to another video on MOSFETs. So in this video we'll see the review of all MOSFET related amplifiers and try to understand their working. So let us start with the N MOSFET. So let us try to understand its IV characteristics. Uh, we know that MOSFET has, this is a cross section view of the MOSFET, which will have a P minus substrate, and there is a N plus diffusion, which will be defining the drain and the source, and we'll have a thin oxide layer on top of that. This is the gate structure. So if you name it as source, so then this is gate, then this is drain. So over here, so we can name this as gate, source, and drain. Especially in case of N MOSFET, for electrons to move from source to drain. So this is the movement of electrons. We want to have first, there should be a channel created for which we are supposed to have a sufficient VGS, which is more than the threshold voltage. So VGS has to be greater than threshold voltage, so that channel is get formed, and this is what is VGS. If you can see, gate is at higher potential than the source, and then we'll have of course, once the channel is established, I want to make the current to flow, for which we are supposed to have one more potential, which is between drain and source. Now you can see drain is at higher potential than source, so this we call it as VDS. So now VDS should be greater than 0 for current to flow. Of course, if VDS is greater than VDS saturation, then we call that current is, we call it as ID saturation. So that's the saturated current. And if VDS is between, if VDS is between 0, suppose if it is less than VDS sat, and if VDS is greater than 0, so here you'll have again the MOSFET will be certainly on, because VGS is greater than VTH. If the VDS is between 0 and VDS sat, we'll have the MOSFET operating in linear region, so you will end up with ID linear. So here it is the linear condition. If you can carefully notice, source is always at a lower potential compared to drain and gate. So this is what is the scenario we want to have for getting the IV characteristics of the MOSFET. So this is grounded. You can call it as VGS. This is VDS because it is applied between drain and source. And if you actually plot the IV characteristics, in IV characteristics we have the drain current in y-axis and VGS as the x-axis parameter. So since you're relating VGS and ID, so this is what is ID here. So we naturally call it as transfer characteristics. So this is transfer IV characteristics. So this will end up with till VGS is less than VTH, MOSFET will be off, and then once if it exceeds VTH, the current starts flowing. So this is for a particular value of VDS, So we have, and of course this is the transfer characteristics where you're relating ID and VGS. That's the current I, V is VGS, and in this particular characteristics VDS is kept constant. So we have one more characteristics, which is the output characteristics, which will have, in the output characteristics I'll have, this is characteristics. So this is VDS versus it is ID versus VDS. So now the plot comes out to be something like this. So this is how you're going to have. This is for a particular value of VGS. This is for another value of VGS, and this is for a bit more larger value of VGS. You can see now this is here desaturated, here it is saturated, here it is almost saturated. So if I call it as VGS1, this is VGS2, this is VGS3. VGS3. One minute. Okay, wait. Wait. Give me 5 minutes time, so I'll come back.